All right, welcome to chapter 20, hypothesis testing is what we're going to start today. And the first thing you need to know is that there will be a midterm. I don't know that it'll be Tuesday, March 9th for sure, but that's around that week probably. These are 12 AP questions that I will have posted on Canvas, and they are AP questions. You should practice them. And I'm actually only going to choose 3 of them for you to answer on that day of the midterm. We will also be taking notes that day. You'll have a time limit of about 40 minutes to do those 3 AP questions, which is slightly longer than you would have for 3 AP questions on the day of the AP test. So it will be these exact questions, 3 of these. You just don't know which ones I'm going to pick. All right, so let's get started with hypothesis testing. You should have your notes, and you should be taking notes as well along with me. So in the last unit, our goal was to create an interval of plausible values for a population parameter. We were doing confidence intervals. Statisticians also use sample data to decide whether a claim or a hypothesis about a population parameter is plausible. So a hypothesis is a claim or statement about the value of a single population parameter. For example, a politician claims the majority of citizens support Social Security reform, so he takes a random sample to see if the data support the hypothesis that P is greater than 0.5. Notice the hypothesis statement is dealing with the parameter P, not P hat. We could also deal with mu, the mean. Now, majority, if you're dealing with voting, a majority is greater than 50%. That's why you are taking a random sample to see if the data support that they support Social Security, so it's greater than 50%. Or we may not trust the claim of Frito-Lay when it says that a bag of Ruffles weighs 14 ounces on average. So we choose a random sample of bags and see if the data support the hypothesis that the mean is less than 14 ounces. So we don't think they actually fill it as full as 14 ounces. So our hypothesis is that the average amount of potato chips in a bag is less than 14 ounces. So note, a hypothesis makes a claim about a population parameter. So P hat or X bar are not appropriate hypotheses. P hat and X bar are characteristics of a sample statistic. A test of hypothesis or significance test is a method for using data from a sample to decide between 2 competing hypotheses about a population parameter. So, for example, you could have P is greater than 0.5 as opposed to P is less than 0.5. So these would be the 2 competing hypotheses. You could have mu is equal to 14 versus mu is not equal to 14. So you are going to be making a decision. You're going to make a hypothesis, an alternative hypothesis. Then you're going to do a test of significance or a hypothesis test using your data from a sample and make a decision on which one of these is more likely to be the truth. So, of course, it would be very easy to determine which claim was correct if we could conduct a census. Unfortunately, this is rarely possible, so we're left with making a decision based on a sample. A good analogy for our hypothesis testing is in the American judicial system. In a trial, there are 2 competing hypotheses. The defendant is guilty or the defendant is innocent, or what we say not guilty. Also, the defendant is presumed innocent until they're proven guilty. So, for example, we would initially believe Frito-Lay is telling the truth about the weight of Ruffles bags until we have convincing evidence that the average weight is less than 14 ounces. That is, when we are convinced that the evidence against Frito-Lay is not just due to sampling variability. All right, so continuing on page 143. Similarly, in a hypothesis test, we initially assume that one of the hypotheses is true. This is called the null hypothesis. Null hypothesis. We then consider the evidence from the sample and reject the null hypothesis in favor of the alternative hypothesis only if there is convincing evidence against the null hypothesis. So the notation, the null hypothesis is denoted H with a little O below it. The null set is like the empty set, okay? So H sub 0, it's sometimes read H naught. So that's the null hypothesis. And the alternative hypothesis is H with a little A, sub A. In the examples above, what were the null and alternative hypotheses? So we talked about innocent and guilty. So the null, the way I'd like you to think of the null is the initial assumption. What do we assume initially? And the alternative is your suspicion. What do you suspect? So with the Frito-Lay, we would initially assume that they actually so let's look at the Frito-Lay example. The null hypothesis would be that the mean is equal to 14. We would assume that they fill it at 14 ounces, okay? But the alternative, what we suspect, is that it's less than 14. So that's our suspicion. Okay, so if we're dealing with the judicial system, the null hypothesis is that they are innocent, and the alternative is guilty. All right, that really doesn't go along with these so much because it just depends on how the person and the case. So in the case of the voting, people supporting I think it's Social Security, the null hypothesis would be that it equals 50%. The alternative, we suspect that there's more, that they actually favor it, so greater than. And you could do less than and greater than. Okay. So in general, the form of a null hypothesis is the null is the population parameter equals the hypothesized value, some specific value. And it's just easier. Your life will be a whole lot easier if you always make the null an equal to something. The alternative hypothesis is one of the following. The alternative could be that the population parameter is greater than the hypothesized value. But you always use the same value, okay? So these values in the null and alternative hypotheses are always the same. It's just the symbols that are different. Or you could have less than or not equal to. But in the null hypothesis, always do equal to. And then based on what your suspicion is, choose one of the three, greater than, less than, or not equal to. So note, the null hypothesis is always equal to, and the hypothesized value is always the same for both hypotheses. So there are two possible outcomes of a test of hypotheses. Okay, the first outcome is you could reject the null. Reject the null. So I might reject that. Or fail to reject the null. So if I reject this, then I'm in favor of this. If I fail to reject this, then I'm saying that the null is actually what we believe to be true. Okay, we reject the null when data from the sample strongly suggests that it isn't true. That is, when we have evidence beyond a reasonable doubt, we don't think the results are due to sampling variability. If the sample does not contain such evidence, we fail to reject the null. That is, we fail to reject the null when the results could be due to sampling variability. Okay, you'll need to be careful when you interpret the results of a hypothesis test. If you fail to reject the null, it doesn't prove that the null is true. It just means you don't have strong evidence against it. That is why defendants are declared not guilty and they are not declared innocent. There wasn't enough evidence to convict them, but that does not mean they are innocent. Thus, we never accept the null hypothesis. We only fail to reject it. All right. So, according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, according to the study, the majority of couples tilt their head to the right when kissing. Define the parameter of interest and state the null and alternative hypotheses for the question. So the parameter of interest would be the proportion of couples who tilt to the right when kissing. So that's the parameter of interest, the proportion of couples who tilt their head to the right when kissing. All right, and state the null and alternative hypothesis. So the null hypothesis, okay, majority infers that we're dealing with more than 50%. So what we'll do is we're going to say that the null hypothesis is that the true proportion is equal to 50%, and the alternative is that what we suspect, okay, we're going to assume that, so the parameter of interest is the proportion of couples who tilt to the right when kissing. So what we assume is that it really doesn't matter, that, you know, it's equal, okay? So then our alternative is that it's greater than 50%. So we, based on this article is saying, hey, more people tilt their heads to the right, okay? So in the study, a researcher observed 124 couples kissing in various public places, found that 83 out of 124, or 66.9% of the couples tilted to the right. So this is my p hat. My p hat is equal to 0.669. All right, so is this convincing evidence that p is greater than 0.5? All right, well, what we need to do is we need to check the conditions. All right, so our p hat is 0.669, so we want to know, is this convincing evidence that p is greater than 0.5? So when you're starting a hypothesis test, you say, well, my sample is greater than 0.669. So you could say something like, since 0.669 is greater than 0.5, it seems that the research is true. But this difference could be due. This difference could be due to sampling variability. So what I'm going to do is I'm going to do a hypothesis test. And actually, we're just going to do a simulation here. We're not going to do a formal hypothesis test today. So what is the probability that we get a sample proportion as high or higher as 0.669 by random chance? This is the way, this is what we're thinking every time we do a hypothesis test. We assume the null is true, and then we say, well, what's the probability we get a sample portion as high or higher than 0.669 by random chance? So that is, if there truly is a 50% chance of observing a couple kissing to the right, what is the probability that in a sample of 124 couples we find 66.9% or more kissing to the right? So let's do a simulation. I actually did a simulation, and I let 0 equal kiss to the right and 1 equal kiss to the left, and what I'm caring about is the kissing to the right. So I did 4 samples, and I got 58 out of 124. They're all right over here. 63 out of 124, 58 out of 124, and 55 out of 124. So each of these, this is 44%, 55 is, and then 58 divided by 124, that's 47%, 0.47, 63 divided by 124, that's 51%. So I got 0.47, 0.51, 0.44. And I want to look at those trials and say, based on those trials, is it possible that more than 50% kiss to the right? So we'll finish this in the next video.